Today we're going to continue to work on volumes of revolution, but now what we're going to look at is between two functions instead of between the x-axis and a function. So this is still from what we did yesterday. So here we have that region enclosed by y equals f of x, so some function from this a value to this b value. Rotating around, we get this shape. Remember, this is kind of like a bowl. Think about it, turn it sideways. It's a bowl, but it's a solid bowl, so there's nothing in the middle of it. So this is our formula for finding the volume of revolution just between the function and the x-axis, because you don't really have to take anything away from it. What we're going to move into now is what happens when it's between two functions. So maybe instead of the x-axis, maybe I'm going to look at having a function there as well. So I'm going to look at this region here. And now this region is going to go around my whole circle. So now you have to look at it that way and go, okay, now what shape do I have? So giving you a nice visual with the shape. So here we have a circle. So if I had this function up here and I have this function down here, what shape would that make when I revolve it around? Well, it makes a donut because this whole piece here is coming around, and then this whole piece here is coming around. I'm not going to be able to draw this very well. And then there's this other circle here, and then we connect it along the way, and we have that shape of a donut. So what we're going to look at is we're going to have to take out this piece here. So we're not going to be able to have that inside piece, because it's not the volume of the whole thing anymore. It's the volume minus the volume of this. Because that's really what we're looking at now, is we have two different pieces. We have the one that's made from here, and then we have the other one that's made from here, and we're going to have to subtract those two amounts. But otherwise, it's using the same exact premise behind it. So if we need to do that, we're going to need to, again, subtract out. So the only change is that instead of, so before, this was my integration. I'm going from a to b of this function. But it was going around the x-axis, which means technically it was subtracting 0. Now, it's not subtracting 0, it's subtracting the height of something else. So that radius is getting, the radius of the whole thing is still all the way out there. But then we're taking away a part of the radius. So then we're going to have to use that part here, that's the radius piece of it, and then be able to subtract that out. And what you'll notice notation-wise, it's the y of the upper minus the y of the lower. And that's the other thing that you'll have to take into consideration, making sure that you know which one's upper, which one's lower. So if we graph this, you do know where they intersect. You know which one's higher than the other one. So it's really nice when they give you a picture. But sometimes the ones that we're going to look at are super complex. You're not necessarily going to know what they are. Maybe you don't have a calculator and you can't do it. So we're going to learn how to take all of that into consideration. So first problem, we're starting out very basic. We want the area, or the volume, that this shape is going to make. So this green shape here is going to make when it revolves around the x-axis. So when this goes around the x-axis. And I've got a 3D picture that I'll show you as well to help you visualize that. But what we have to do is we have to know what we're integrating with respect to. So from where to where. Okay, so I'm starting at this value, I'm ending at this value. That's the volumes piece that I'm looking at. So this shape only goes from 0 to 1. That's it. I can't go to 2, I can't go to 3. I have a definite beginning and end that I'm going to work with because that's where they intersect. I'm not going to get, doesn't make sense to have a volume anymore because now they no longer have the same upper or lowers anymore. Now if I wanted to, I could revolve this shape around and this one keeps going forever this way. That's a whole nother situation. Okay, still completely doable. But for this one, it is completely bound between these two pieces where the functions intersect. So what we're going to do is we will find the volume that this one makes. So that's kind of like that bowl going all the way around. But then what we're going to have to do is we're going to have to find the volume that this one makes. This one, just real quickly, makes kind of like this cone shape. So we're going to have to find the volume of that. And again, that's kind of in essence with respect to x. But we'll do the both at the same time, and we're just going to subtract them. If you really wanted to, you could do each of them individually and subtract them out. But what we're really looking at is we're finding what are called washers. And I'll show you that with the next picture. We're trying to take out that piece so we can do it all in one step instead of having to do each of them individually. Okay, so therefore, just like before, we are going to integrate from 0 to 1. And then, remember, it's pi r squared h as h approaches 0. So therefore, pi goes outside. My radius, so what I'm going to look at is the radius of my upper. So that's the y of my upper. So that's x squared, or square root of x. And then that's squared minus the radius squared of my lower, or inner, is this one, which is x squared. And then that's squared. And that's dx. So now I'm going to simplify that, and then we are going to evaluate it. So this is pi times the integral from 0 to 1 of x minus x to the 4th dx. So integrating this, we get x squared over 2 minus x to the 5th over 5. Pi is times this, and that's from 0 to 1. So then I just plug each of those in. That's pi times a half minus a fifth minus 0 minus 0, which therefore gives me pi times a half minus a fifth, so that's 3 pi over 10 units cubed. Upper, the radius of the upper squared. Again, the radius is based on the y value. That's how high it is. That's the radius to the x-axis. Minus, oh, I flip-flopped that, sorry. So the radius of my higher is this one here, squared minus the radius of my lower, which is this one here. And then we square each of those, and then we integrate just like normal. Again, this problem, I gave you the stuff you needed, but realistically, you can do this. You found points of intersection. You know how to find which one's upper and lower, and that's really the premise of what we're going to do. You're not always going to be given this. Sometimes you will. More likely, you're going to get, oh, sorry, I did want to show you this. Okay, so this was the upper one. So this is the red one. So that's, like over here in this shape, that's this red going around the outside. But then there's this green one, and again, like I said, the green one kind of goes like that. So therefore, the green one ends up being this inside piece here. And what we're doing is we're finding washers. So that's what we're doing is, this is called the washer method, because what we have to do is we have to subtract out the green part. So that's what this is here. So this darkened circle is the red going all around it. And then this inner part is the green that we have to subtract. So there's an infinite number of washers that we're adding up, remembering that our H value is approaching 0. So that cylinder, that height there is approaching 0. So that's why this is called the washer method, because I'm taking a whole bunch of washers and sticking them on top of each other and finding each of their individual values, which means I've got to find the area of the outside and the area of the inside. That way I can subtract those heights to figure out what my actual value is. So these three are nice pictures here. And this is just kind of giving you like trying to give you an idea of what the shape looks like. Okay. So in this next example, this is a very typical type of problem that you would see where you're looking at the region bound by curves. So I have these two graphs. Now, part of this is going to be like being able to sketch these graphs out and knowing what the graphs look like. Now, I know this one opens up. I know this one opens down because this is just y equals negative x squared plus 8x. So having an idea of that is helpful. Also, I know this is a parabola that moves 6 units up, so it's something like this. This is a parabola that opens down. It goes through the y-axis, so it's going to be something like this, which means, I know it's not a big region, I'm going to find that shape there that's going to revolve around the x-axis. So that's the shape, in essence, that we're looking at. So what I need to do is I have to be able to find what this value is here and this value is here, so I can integrate it on those bounds. So I have those endpoints to work with. So therefore, step one, you need to find the intersection. So they're telling us what our volume of revolution equation is, which is nice. but we just have to get to that point. So I need to find this point of intersection and this point of intersection. How do we find an intersection? We set them equal to each other. So therefore we solve and we get 2x squared minus 8x plus 6 equals 0. I can factor out a 2, which then gives you x squared minus 4x plus 3. And now I can factor that, and that factors into x minus 3, and x minus 1 equals 0. Therefore, they intersect when x is 1 and at 3. What we just did is we found that part there. We found the integration, like the bounds. Okay, so now I need to keep going with this, and I need to set up my formula. So the other part that you have to figure out is which function is higher than the other one. And sometimes you might not know. Okay, you may have no idea. Maybe the shapes are kind of goofy. You're still trying to figure it out. So here's my recommendation. You know it goes from 1 to 3. If it goes from 1 to 3, pick a number like 2. Plug 2 in for your x here. Plug 2 in for your x's here. Figure out which y value is bigger. That's the one that's on top. That's the upper one. So again, if you have no idea what the shape looks like or any of that, pick a number that's in between your bounds. And then that'll give you an idea of which one's upper, which one's lower. So therefore, we know our volume is pi times the integral from 1 to 3. We just found that. Now I need to set up each of my pieces. So I know my upper is this one because this is the one that was higher. Or if I plugged in 2, this gives me my bigger number. So therefore, it's negative x squared plus 8x minus x squared plus 6 dx. Oh, and then I square these two, sorry, because it's my radius squared. Okay, so now, continuing on, this is equivalent. It's a show that problem, so you got to show your work. Integral from 1 to 3. I've got to square this, so therefore it's negative x squared plus 8x times negative x squared plus 8x. So you're doing this, and you are expanding. So therefore you get, when you do that, x to the 4th minus 16x cubed plus 64x. And then when you square this, again, you do both of those pieces. So we're subtracting, and then this is x to the 4th plus 12x squared plus 36 dx. Okay, continuing to simplify. That gives us pi integral 1 to 3. And then combining all those like terms, so my x to the 4ths go away. I end up with negative 16x cubed plus 52x squared minus 36 dx. Okay, let's integrate that. Oh, nope, we wanted to show it. It was a show that problem. We'll evaluate the volume in just a moment. So it's not quite the same. So if you notice, the only thing that we don't have is this 4 outside here. So do you notice that you can factor 4 out of all of those terms? So that leaves me with smaller numbers. Tend to be helpful. It makes my evaluating the volume much quicker. So that would be negative 4x cubed plus 13x squared minus 9. And then the last thing, just to show that it is equivalent, is just flip-flopping the order. Not a big deal at all. Sorry, my integrals are getting messy. Ooh, yeah. Okay. Okay. So there is my integral statement. Okay. Now I have to evaluate this. So in order to evaluate this, I need to evaluate the integral. Okay. So this gives me 13x cubed over 3 minus 4x to the 4th over 4 minus 9x. All of that is multiplied by 4 pi, and that is evaluated from 1 to 3. Therefore, just the math starts to get a little bit messy as you go through here. Come it's not very complicated. It's just evaluating your integrals just like we normally do. So if we'll leave this 4 pi outside here, we don't want to multiply that through. And then I first will put my 3 in, so this is 13 times 27 over 3 minus 4 times 81 over 4. Oh, that simplifies. Minus 27. And then, so that's the first one. Now I put 1 in. That's 13 over 3 minus 1 minus 9. That gives us 4 pi times, so this whole thing here is 117. That's 81 minus 27 minus 13 thirds. That's a minus 10, so minus that is a plus 10. Leaving that pi out, that 4 and the pi out, so 4 pi. All of this inside here simplifies to 14 and 2/3. Therefore, leaving it in terms of pi would be 58 and 2/3 pi, which is approximately equal to 184.307. So that is the volume of the shape rotated about the x-axis based on the intersection of these two, which was this little shape inside there. Okay, so think about all the stuff that we just went through. Make sure that you have your starting and end point, those x values that you have, and then integrating it, and then at the very end, make sure you substitute in those definite beginning and ends.